Welcome back. This is our fourth and final video for the Quiz 5 solutions. In problem 4, we're told we have a planar lamina, and it's going to rest over this annulus A. Okay, so it's this gray ring here. We know that the ring has an inner radius of 3 and the outer radius of 4. And the lamina has a non-constant density function given by x squared plus y squared. And the goal is to set up an iterated integral in polar coordinates that will give us the mass of the lamina. So the important, of course, first thing is to remember if we want to compute the mass of a two-dimensional object and we have the density function, then the mass is going to be the double integral over the domain, right, over which that object lies, of the density function. Okay. Now, the name of the region is A, and there's a dA here, and so you might think, oh, there must be some connection, and not really. The A is just a coincidental letter there. Okay, so we want to set up this double integral, but we want to do it in polar coordinates, which means we're going to want to write down A not as a type X region or a type Y region, but actually as a polar region. And ideally, even a polar rectangle, right? That's the best case we can think of here. So let's see if we can write A in that way. So we want to write it down in r theta coordinates, where r is the so-called radius. That's the distance from the origin. So you choose some point, any point in here, and you want to know how far away it is from the origin. Okay, that could be your r. And we could see, well, if you're in this gray region, you're more than 3 away, but less than 4 away. Right? So the r is going to run between 3 and 4. Okay, how about the angle? Well, the angle is the angle that this ray that goes from the origin out to your point makes with the positive x-axis. And because we have the entire ring, we can get any angle between 0 and 2 pi. We don't go past 2 pi because, well, then we'd be repeating. So the theta can be anything between 0 and 2 pi. We can go all the way around. And you know, this is a very nice polar rectangle, right? If we liked, we could write it in this form, 3, 4 cross 0, 2 pi, where we have to understand here, we're not talking about x, y coordinates, but polar coordinates. All right, well, now we can actually set up our integral. So let's say we'll do the r's first. R goes from 3 to 4. Then we'll do our thetas. Those go from 0 to 2 pi. And now we need our rho. Okay, our rho is x squared plus y squared, but that's given in rectangular coordinates. So we need to put this into polar coordinates. But x squared plus y squared, that's a great one, right? X squared plus y squared is equal to r squared, right? That's the distance from the origin, really. At least the square of the distance from the origin. So I can put an r squared in here for my rho. And now I need my dA. And we might be thinking, okay, cool, so dr d theta, right? Or maybe here, because the theta is on the inside, d theta dr. Well, we could do that, but we wouldn't be right. Remember, the area of a teeny polar rectangle, right? A little differential rectangle is not d theta dr, but actually r d theta dr. So we actually have to include an extra r in here. This is what I call the cost of doing business. When you switch from rectangular into polar coordinates, your dA isn't just as simple. You actually have to remember to include an extra factor of r. Okay, so now we have this r cubed as our integrand, which has nothing to do with theta. So we can actually pull it out. Fantastic. Pull out the r cubed, and I'm left with integrating d theta from 0 to 2 pi. Like, that's fantastic because there's just a 1 integrand, right? This just gives me the length of the interval, which is 2 pi. Okay, so I can pull the 2 pi out, and now I'm integrating r cubed. Well, r cubed, let's see, with respect to r, that's going to be r to the 4th over 4. And we'll evaluate from 3 to 4. Okay, well, we get 4 to the 4th over 4. Okay, that's same as 4 cubed, which is 64. Minus, okay, now I get 3 to the 4th over 4. Well, okay, that's just 81 over 4. And you know what? That's as good of answer as any, right? Okay, yeah, of course you could distribute this and blah, 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 blah. I don't want to. Can't make me. I'm not going to do it. All right. So what are the takeaways? Hey, mass. We can find mass by double integrating the density function. Second, if we're doing some sort of circle, right, or portion of a circle, really good idea to try to switch to polar coordinates. Of course, this problem even tells you to do so. Set up your polar rectangle, okay? And then when we integrate, man, do not forget that cost of doing business. That dA needs to have that extra factor of an R. All right, take care, everybody. So long now.